So what is information? I mean, it seems like a pretty simple question, right? We talk about it all the time. We get information, we share it, we're worried about misinformation. But have you ever really stopped to think about what that word actually means? Let's really dig into this because the answer, well, it's way more surprising and profound than you might think.
Right off the bat, our own language kind of trips us up. See, on one hand, you might say something like, if I get the information that it's raining, well, then I know it's raining. We treat information like it's the same thing as truth. But then, in the very next breath, we'll talk about spy agencies spreading false information. So, which one is it? Can information be false, or is it true by definition? This little paradox is pretty much the starting point for our entire journey.
Okay, so to unravel this whole thing, we're going to trace the story of information. We'll start with that paradox we just talked about, then see how the idea first took shape way back in ancient philosophy. Then we'll jump forward to how scientists figured out how to actually count it. From there, we'll meet the revolutionary bit, uncover information's true size, and finally, we'll ask what all of this might mean for reality itself.
All right, so let's tackle that central puzzle head-on, the information paradox. We use this word constantly, but how can it mean so many completely different, even contradictory things?
You know, this modern idea we have of information as some kind of abstract stuff that's just flowing through our phones and the internet, it's actually pretty new. It really only came about with the rise of mass media and intelligence agencies in the 20th century. Before that, the word meant something much more concrete and, honestly, a whole lot more interesting. So if our modern take on information is new, what was the original meaning? Well, to find out, we've got to go back, way back. We need to see how this idea first took form. The clue is right there in the word itself, information. For ancient philosophers like Plato and Aristotle, this was a huge concept. Information wasn't some thing you had. It was the very act of giving something its form, its structure. An idea didn't contain information. The idea was the information that literally shaped your mind. This concept evolved over centuries with thinkers like Augustine and Locke, but that core idea stuck around. Information was about structure, not just data. Aristotle had this absolutely brilliant way of explaining it. He said to think of our minds like a piece of wax. When a signet ring presses into it, the wax takes on the ring's form, its unique pattern, but not the actual gold or iron it's made of. That's what it means to be informed. A pattern from the outside world gets impressed upon your mind. But, philosophy can only get you so far. For science and engineering, you've got to be able to measure things. So how do you go from this abstract idea about form to an actual number? Well, that's the big challenge of our next step, counting the unknown. To build a real mathematical theory of information, scientists figured it had to have two key properties. First, it had to be extensive, which is just a fancy way of saying it has to be additive. The information in two separate books should just be the sum of their individual information. Makes sense. Second, it has to reduce uncertainty. A message that tells you something you didn't already know makes you less uncertain about the world. The trick was finding the right mathematical tool for the job, and that first property, additivity, pointed directly to one perfect function, the logarithm. You might remember from math class that logs have this almost magical ability to turn a multiplication problem into an addition problem. That was a huge insight. If you could model information using logarithms, you could make it add up properly. And that one insight, that logarithms were the key, paved the way for one of the biggest scientific breakthroughs of the 20th century. It came from an engineer named Claude Shannon, who gave us the bit and the message. So back in 1948, Claude Shannon, an engineer at Bell Labs, put all these pieces together, and his idea was totally revolutionary. He said the amount of information in a message has nothing to do with what it means. It has everything to do with how surprising it is. The less probable a message is, the more it surprises you, the more information it contains. And he even gave us a unit to measure it with, the bit. His formula there simply puts that core idea into math. Think about it this way. If I tell you, the sun will rise tomorrow, are you surprised? No, not at all. The probability is basically 100%. Because it's so predictable, that message doesn't reduce your uncertainty about anything. It's not news. According to Shannon, it contains pretty much zero information. But what if the message you get is, you just won the lottery? The probability of that is astronomically low. It's a total shock. That message is jam-packed with an incredible amount of information because it just completely shatters your expectations and fundamentally changes your model of the world. That right there is the simple genius of Shannon's idea. But as absolutely brilliant as Shannon's theory is, it does have a curious blind spot. And to see it, we need to look past probability and towards something a little deeper: complexity. This is where we start to glimpse information's true size.
Okay, take a look at these two strings of bits. The one on the left has a really simple, obvious pattern, right? 5 zeros, then 5 ones. The one on the right looks a lot more random. Here's the catch. Because they both have 5 zeros and 5 ones, Shannon's theory says they contain the exact same amount of information. And that just feels wrong, doesn't it? The patterned one seems so much simpler.
This is where another genius, a mathematician named Andrei Kolmogorov, stepped in with an even more powerful idea. He basically said, forget probability. The true amount of information in something isn't about surprise. It's the length of the shortest possible computer program you can write to generate it. Think about that for a second. It's all about descriptive simplicity. This idea is called algorithmic complexity. And the number pi is the absolute perfect example of this. If you look at the digits of pi written in binary, they look totally random. According to Shannon, they'd be packed with information. But Kolmogorov would look at it and say they contain very little information. Why? Because you don't need to write out all those digits. You can just write a tiny, elegant little computer program that can generate them forever. The information isn't in the random-looking string, it's in the simple code that creates it.
So, where has this incredible journey taken us? I mean, we've gone from ancient philosophy all the way to modern computation. Now we can try and put it all together and think about the final, mind-bending picture, the code for reality. We've seen this concept of information basically transform 3 times. It started out as a philosophical idea about structure, or form. Then it became a mathematical tool for measuring surprise and reducing our uncertainty. And finally, it evolved into this incredible computational measure of complexity, the length of an object's shortest possible description.
And this leaves us with a truly wild final thought. If Kolmogorov was right, if the ultimate measure of information in anything, a rock, a star, a living cell, is just the length of the shortest program that can describe it, well, what does that imply about our universe? Is it possible that all the staggering, beautiful complexity we see around us is just the output of a surprisingly simple, maybe even elegant piece of code?